We write down Bowser's speed 64.4 km per hour times the conversion factor for units of length and the conversion factor for units of time. Thanks, Wu. We have 64.4 km per hour times 1000 meters over 1 kilometer times 1 hour over 3600 seconds. After solving it, we get 17.9 meters per second. After Bowser got struck by lightning, his speed was reduced to 17.9 meters per second. When we calculate the speed of a moving object, we divide the distance traveled by the time taken. Let's suppose Bowser is driving in the Bowser Castle circuit. After he finished the first lap, his speed was 92 km per hour. We divided the length of the track by the time taken to finish that lap. Does that mean his speed was the same along the track? That's not necessarily true. In that first lap, let's say Bowser got a mushroom. He used it and sped up. Because of that boost, his speed wasn't constant throughout the lap. These are two different types of speed. When we consider the entire lap, it's called average speed. It describes the object's speed over a long period of time. When we consider only a specific instant during the race, it's called instantaneous speed. It describes the object's speed at a particular moment. The shorter the time interval, the better the approximation. This different speed leads us to the next physical quantity, acceleration. Acceleration is defined as a change in velocity over time, or mathematically speaking, a equals final velocity minus initial velocity over time. Notice that acceleration depends on two things: how much the velocity changes and how long that change takes. As you can see in the equation, if final velocity equals initial velocity, the numerator is 0, so there's no acceleration. In other words, we have a constant or uniform velocity. Back to Bowser. Let's suppose that right after he uses a mushroom to accelerate, his speed goes from 92 km per hour to 120 km per hour in 0.5 seconds. What's his acceleration? We solve the equation a equals final velocity minus initial velocity over time, where final velocity is 120 km per hour, the initial velocity is 92 km per hour, and t equals 0.5 seconds. It's important to note that we can add or subtract physical quantities that have the same units. In this case, we can subtract 120 km per hour and 92 km per hour because they have the same units, kilometers per hour. We have a equals 28 km per hour divided by 0.5 seconds, which gives us 56 km per hour second. Those are some strange units. What is their meaning? That answer tells us that Bowser increases his speed by 56 km per hour every second that passes. If he keeps the same acceleration, after 1 second he will increase his speed by 56 km per hour. After 2 seconds, his speed will have increased by 112 km per hour. After 3 seconds, his speed will increase by 168 km per hour, and so on. Let's have a look at that equation again. We can work out the acceleration units by observing the physical quantities involved. We have speed units divided by time units. If we take the last answer, the acceleration Bowser had was 56 km per hour second. Let's convert 56 km per hour into meters per second. As always, we let Boo bring the conversion factor and we solve. 56 km per hour times 1000 meters over 1 kilometer times 1 hour over 3600 seconds. We end up with 15.6 meters per second. Back to Bowser's acceleration. It was 56 km per hour per second, and 56 km per hour is 15.6 meters per second. Substituting this value gives us 15.6 meters per second, which is 15.6 meters per second squared. It's more common to use the same unit for time. If we use seconds to measure speed, it's common to also use seconds when we measure acceleration. What's the meaning of those units? 15.6 meters per second squared means that Bowser's speed increases 15.6 meters per second every second. After Bowser used lots of mushrooms, he got into first place in the last lap, but suddenly a blue shell hit him, and Mario, Luigi, Peach, and even that cheater Yoshi overtook him. I hate when it happens. Bowser's speed was 92 km per hour before the impact, but now it's 0 km per hour because the blue shell stopped his car. Even when a moving object comes to a stop, it still has an acceleration while it's slowing down, and it's because of that change in speed. Let's calculate Bowser's acceleration in this case. We convert 92 km per hour into meters per second to fit the speed units in with the time units, and we get 92 km per hour times 1000 meters over 1 kilometer times 1 hour over 3600 seconds, which is 25.6 meters per second. Now let's assume the time it takes the blue shell to stop a car is 0.3 seconds. Bowser's acceleration is then final speed 0 meters per second minus initial speed 25.6 meters per second over 0.3 seconds. The final answer is A equals negative 85 meters per second squared. We got a negative acceleration. This is often called deceleration, and it happens when a moving object slows down. If you remember that velocity is a vector and speed is a scalar quantity is a magnitude, while a vector is a magnitude with direction. Acceleration is a vector, just like velocity and displacement. We've learned so far that acceleration is a change in velocity divided by the time interval. It's a vector and it can be positive or negative. Let's put Bowser now in the Baby Park circuit. He finishes the first lap with a constant speed, let's say 25.6 meters per second. That means that speed didn't change along the track, but Bowser accelerated in the same first lap. How is that possible? He moved at a constant speed, yet he was accelerating? Let's go back to the definition of acceleration. Acceleration is a change in velocity divided by time. There it is, change in velocity. Velocity can change if we speed up or slow down, but also if we change direction. If either the speed or the direction or both is changing, then the velocity is changing. Bowser had to change direction to round that part of the track, so even if his speed was constant, his velocity was not, and that change in the velocity means there was also an acceleration. This is the end of the video. Here are some questions for you. If you enjoyed this video and learned something new, don't forget to like and subscribe. It really helps the channel grow. See you next time.